matrices. Okay, so a single one is called a matrix. If you see it written like this, matrices, that's the plural form. Okay, same thing. What is a matrix? Okay, so as you can see on the top where it says definition, a matrix is simply a rectangular array of numbers. It will be written with rows and columns, and it will have the big brackets around it. Okay, if you see this, this is a matrix every single time, right? The order of your matrix, it always is labeled, and they will ask you what are the dimensions. So when you talk about the dimensions of a matrix, it is always rows, then columns. The easiest way for me to remember that, because sometimes I even get like, what is a row and what is a column? Columns have L's in it, so those are the up and down L's. That's a shortcut way to remember it. Rows go across. In English, how do we read?
Left to right.
Left to right. Okay, so we're going to do everything on the left, and then we're going to go to the right. Okay, this is how I remember what order they go in. Okay, so if we were to write the dimensions of this one, it has how many rows?
3.
It has 3 rows, so it is a 3 by how many columns?
4.
3 by 4, okay? So in this it says if a matrix has n rows and n columns, it would be an m by n. So you're going to count the number of rows first, and then you're going to count the number of columns. It will always be written as 2 numbers with an X, which is also the by symbol, like a 2 by 4 if you went to the lumber store. 3 by 4 in this case, okay? There are 5 different types of matrices. A square, if it's square, that means your numbers are the same. So a 2 by 2. Or it could be a 4 by 4, correct? Okay. Square simply means it is square. It has the same number of rows, same number of columns. Okay. There is a column matrix, which means it is simply one column. It will look like this. This is a what? A 3 by 1. 3 by 1. Okay? A column matrix is a column. One column up and down. A row matrix, what do you think?
1 row.
Is 1 row. It could have one term, multiple terms. In this case, this is a 1 by 3. A 0 has zeros. Okay? Pretty simple. Identity matrix, so this is a special one. No matter how big your identity matrix is, it will have ones along the diagonal and zeros everywhere else. So if it's a single, it would just have a 1. If it's a 2 by 2, you're going to have a 1 and a 1 along the first diagonal, and you're going to put zeros in everywhere else. If it's a 3 by 3, you'll have ones along the diagonal, that first diagonal, and then you're going to have zeros everywhere else. You can figure out 4 by 4. Okay, these are identity matrices. Does not matter the size of them, doesn't matter the dimensions. You will have ones along the first diagonal. Okay, those are different ones that you're going to need to know. When we name a matrix, it is always, you will never see it otherwise, it is named with a capital letter. Typically, they start with the letter A. We work through the alphabet. So if you have another one, it would be B. So they are named with a capital letter. It would say A equals. Right? The different parts of your matrix are called an element or an entry. Okay, so on that first one, some terms will say elements, some terms will say entries. Again, we always move from left to right. So if they ask, for that first part, it says, we already know it's a 3 by 4 matrix. The entry 2, 3, 2, 3, this is going to be your row and your column. Row 2, column 3, that entry is what? 5. The number would be 5. What would be your entry 3, 1? On your example, or up here?
-8.
-8. -8 would be 3, 1. Perfect. All right. Number 1, interchanging rows. Okay. On a matrix, you can interchange anything. You can multiply it. We're going to go through the different things. So why would you use a matrix? What is it? It is a way to organize data, organize information. So you might have a store and you have hoodies and basketball shorts and jerseys, right? And you have small, medium, large, and extra large. And these are the quantities you have of all of that. Okay? So it is simply a way to organize data in a chart. All right? Got it? Am I embarrassing you?
No.
I smile at you? Okay. So that is why we use them. What is great is that if you have matrices that are the same size and exactly the same, they are called an equality. So if I wanted the equal matrix to A, I would simply rewrite this exactly the same. Now, you can do different things to a matrix. You can add them together. We can multiply. We can subtract them. Okay, so we're going to go through the different parts of it. So number 2, I'm just going to quickly say, it says multiplying rows by a non-zero constant. If we were to multiply row 2 by the number 2, what would we put in there? So I'm multiplying just this row by the number 2, by -2.
8, 4, 10, 16.
-8, -4, -10, -16. All right? So, what?
That's just it.
That would be it.
So you can put that in.
Yep, you can fill that in on your notes. All right. So operations with matrices on the back.
Was -2? I'm sorry.
Yeah, so -2. We just did, they asked you to multiply the whole row 2 by a -2. So it'd be -8, -4, -10, -16. All right, so if we have 2 matrices, I'm going to do another one up here. 1, 2, 3, 4. I have 1, 2, 3, 4. What are the dimensions of these?
1 and 2. I'm sorry, 2 and 2.
2 by 2, 2 by 2, okay? They're both 2 by 2. Each space has the exact same number. Are these matrices equal? Yes. These are equal. They're called equality. Now, if I have 1, 2, 3, 4, I still have a 2 by 2. I have all the exact same numbers in there. Are these matrices equal? No, they are not equal. To be an equality, every entry has to be exactly the same. Got it? Pretty straightforward. Okay, now, if we are going to, we're going to leave these little ones up here. If we want to add a matrix, add 2 of them together. Okay, number 1, they have to be the exact same size. They both have to be a 2 by 2, or a 3 by 3, or a 4 by 7. Their dimensions must be exactly the same. The reason is, when we add corresponding places. All right? So what would be our new matrix if we added these two together?
2, 5, 5, and 8.
Perfect. 2, 5, 5, and 8. You're going to add the ones in the exact same placeholders. The exact same entries would be added together. Right? Now, if we subtracted them
0,
exactly the same, 0,
1. Oh, wait.
-1.
-1,
Then 1.
1,
And
0.
0. Okay, is this an identity matrix?
No.
No.
Because it has to be 1.
It has to be ones in the very first spot and along the diagonal.
so it's not another word for it? There's just.
Nope, this is just the answer.
No, like there's identity would be the one if it went the middle. This is just.
Yeah, if they said subtracting these two matrix gives you an identity,
It's a square.
the answer would be no. It does not. This is not an identity matrix.
It's a square.
It's just simply an answer. It's a 2 by 2 answer. It's not an identity. All right. Now, so there's addition, subtraction. If you have a matrix, we're going to keep using our 1, 2, 3, 4. Okay. There is a word called a scalar. Okay. Scalar simply means a real number. Okay. Have you ever used like Photoshop or some sort of graphic or anything, or heard like we're gonna scale this down on a copier? You've got 100%, or you're gonna scale it down, or you're
Stretching it and making it.
or scale it bigger. So now it's gonna be 150%, whatever. Scaling can be used in a way of making something bigger or smaller. You're just multiplying, you're adjusting the size of it. So I try to tie in why they're calling it scalar. Scalar is simply a number that you are multiplying the whole matrix by. Okay? So if we put a 2 out front, 2 times this matrix, it means that we are multiplying. These almost look like parentheses, right? They're the, remember when we learned parentheses, brackets, braces? So these are our brackets. If we were to distribute with a parentheses, we distribute the number on the outside to what?
The first and then the second. And
The first, the second, the third. Each entry, right? Each part of our equation. In the same way, if we have a number on the outside, this is called a scalar. We are going to scale this matrix bigger. In this case, if it was 1/2, we would be scaling it smaller. It goes to each entry. So our new answer would be
2,
4,
4,
6, 8.
2, 4, 6, 8. So we have doubled our matrix, right? Because we've scaled it times 2. Make sense? If you see a number in front of a matrix, all you do is multiply it times every entry in it. Got it? Okay. Matrices work in the same order of operations. Let's do this. Same order of operations as regular math. So what do? We have PEMDAS, right? Or PEMDAS. Okay. Parentheses, we're good. We don't have an exponent. We have multiplication. Which part do we do first of this?
First.
We're going to multiply times 3 first. So we have 3 and 6. Now we have 1 and 2. Can we add these two? Are they the same? We've got a 1 by 2. Sorry. We have a 2 by 1 and a 2 by 1. They are exactly the same. Therefore, we can add them together. When we add the same units, right? So our answer is 4 and 8. Right? Are you ready to take a class picture?
Yes,
Okay.
We're missing a student.
We are missing one. Okay.
can do it after spring break. I'll make a note,
Okay,
and hopefully everybody will be here.
Yeah.
Okay, I'm gonna take a couple candidates.
okay, awesome. All right, does that make sense? Now, here's the confusing part. Well, not really confusing. Now that we understand what matrices are and how we can work them, how we add and subtract, pretty simple. Are we confused on adding and subtracting?
No.
Okay, we have a couple of properties that can work. So on page 3 you can see it says different properties. If we have a scalar multiplied through, or we have 3 different matrices that are multiplied together, they can be grouped differently. So we have matrix A, B, and C. We can multiply the first 2 first, and then the third, or we can multiply the second 2 and then the first. Okay? All of that can work together. Now, we can also, if they were added, you can see it says the distributive property, we are going to distribute and multiply in the same order, just like if these were regular variables. Right? The thing you cannot do, only if they are inverses of each other will this work. You cannot multiply A times B and expect it to be the same as B times A. You cannot have the commutative property of multiplication. You can have the commutative property of addition, but you cannot have the commutative property of multiplication. This is almost always not equal. Okay? So if you're doing something and you're like, oh wait, it's not turning in, I'm not getting the right answer, make sure that we are doing them in the right order, according to what they are asking you to do. Because this almost always is not true. And I'm going to show you why here in a minute. Alright, so multiplication. I'm going to get rid of this one. We're going to work with a little bit smaller one. We're going to start with a 2 by 2, and then we're going to work our way up. So we're actually going to start with number 2 first. When you have matrix multiplication, you will often see it with a little dot in the middle. You may not see it with a dot in the middle. It may just be butted up just like 2 parentheses that are together. Okay? They may write A times B to tell you what to do, and they've labeled different ones. All right. So, a couple of rules with matrix multiplication that we need to go over. Number 1 rule. You always write down your dimensions, because there's some rules that come with it. So let's do our first dimension.
2 by 2.
2 by 2.
2 by 2.
2 by 2. Okay. To multiply. The reason I'm going to show you this, they will say verbally the number of rows in your first matrix must match the number of columns in your second, or the number of columns in your first matrix must match the number of rows. They'll say things like that. What you need to know is the definition is the number of columns. So here I have, we'll do column A and B, or 1 and 2, we'll do 1 and 2. Must match the number of rows, 1 and 2, for you to be able to multiply. If you are to write them out, these inside numbers must match. Right? They must be equal. And your answer will be your outside numbers. Okay? So the inside numbers are both 2. That means I can multiply. The answer that I come up with will end up being a 2 by 2 matrix. So that's your way that you check. You always write your dimensions. Your inside numbers will match. Now, if we have this, can we multiply these?
No.
Well, let's see. We're going to write them. The first one is a 2 by 2. The second one is a
2 by 1.
2 by 1. Do my inside numbers match?
Yeah.
Yes, I can multiply this. My answer will be a
2 by 1.
2 by 1. Right? So I will end up with just 2 answers. Okay. Can I multiply a 3 by 4 and a 4 by 2?
Yeah.
Yes. My answer will end up being a
3 by 2.
3 by 2. Right? So when you write your dimensions out, this is your easy way to check. You will also see written the number of columns of your first one must match the number of rows of your second one. Okay, so now that we know we can multiply these, we can actually move forward. So how do we actually do it? Okay. This requires, so I use colored pencils. You can block it off if you need to, if it gets bigger, okay? The first one, we are going to take the entire first row and multiply it by the first column, right? The way we do that is we multiply each entry, and then we're going to add them together. So we're doing number 1 and number 1. So 3 times 2,
6.
we have 3 times 2, okay? And we are going to add that to 1 times -1, which is -1, correct?
So -6.
So I already know this is why it's nice to go ahead and write out, go, okay, I can multiply. My answer is going to be a 2 by 1. I need 2 spaces. My first space is 6 minus 1,
5, sorry.
5. Perfect. Right? First one's taken care of. Now, we move our way down. We're going to move to the second row. So now I multiply the second row times my column. 0 times 2. We start with our first one. 0 times 2 is
0.
0. -2 times -1.
-2. No, +2.
+2. So 0 plus 2,
2.
2.
So if you have 2, if there's another
We're
column.
gonna add it. Okay. 2 by 2 by 2 by 1. We just worked through 2 problems. We got a new answer. This is our answer. Okay. Got it? Okay. Let's add one. Now we're gonna do 1, 2, 2, 1. Okay. Now I have a 2 by 2 multiplied times a 2 by 2. Can we multiply them?
Yeah.
Yes. My answer will be a
2 by 2.
2 by 2. So I'm going to have 4 spaces. We're going to work through each of our spaces. Okay. For the first space, I need the first row and the first column. All right? So for the first space, so I've got first row, first column. So I have 3 times 1. We can put it here. So I would have 3 times 1 plus 1 times 2. See how we got those? First row, first column. So I'm dealing with first row, first column, first numbers, second numbers. Right? We just work our way down. Multiply these two, add them to multiply these. So 3 times 1 plus 2 times 1 gives us
5.
5. My answer for that first space is 5. Okay. This one, I need first row. What column is this?
Second.
Second column. All right, so we're going to do the same thing again. First row, second column. All right, so now all I'm dealing with are, got that, Nathan? Okay, first row, second column. So we start and we work down. 3 times 2
6.
is my first one, and I'm going to add it to
1.
1 times 1, so I have 6 plus 1 gives me 7. Okay, so what do we think this one is going to be?
Second column by
Second row,
Wait, yeah.
first column,
Oh, yeah.
right? It's in the second row, the first column. So now, do I need to work with 3 and 1 anymore? Nope, I moved down. So second row, first column. Start with the first one. What is my first entry? 0 times 1.
0.
Okay? I'm going to add it to negative 2 times 2.
Negative 4.
Negative 4. So my answer is negative 4. Okay?
Wait.
Second row, first column. I'm only dealing with these numbers. First entries, second entries. Got it? Okay. This one, second row, second column. That's the space it's in, right? It's in the second row, it's in the second column. So I need my second row and my second column. What would be the first one?
0 times 2.
0 times 2, added to
Negative 2 times 1.
negative 2 times 1. Perfect. So we have
Negative 2.
negative 2. So your answer is 5, 7, negative 4, negative 2. All right? If you've never seen this before and they ask you to multiply and they give you answers like that, you're going, where did those numbers come from? Okay? Do you see how that works? When we're multiplying, we have to multiply every element from those sections. We're going to add each of them together. Got it? All right, so now let's do that number 1 together. And what I want you, I'm going to write up here, is we're going to walk through which of the different sections are. So what are the dimensions of the first one? 3, negative 2, 5, negative 1, 4, negative 3. What are the dimensions of that one?
2 by 3.
It's a 2 by 3. What's the second one?
3 by 2.
A 3 by 2. Can they be multiplied?
Yep.
Yes, they can be multiplied. Our answer will be
A 2 by 2.
a 2 by 2. So I will need 4 answer slots. It is perfectly acceptable to set up your paper like this so that you know exactly what you're looking for. Okay, so let's write out what we are actually adding in that. So in the first one, so I have my first row, my first column. What are the numbers that we are going to have there?
3, negative 2,
3 times,
negative 2. Oh, wait.
3 times 1, plus
Negative 2,
times,
3.
no,
Wait,
we're
oh,
going,
column. Negative 4.
negative 4, perfect,
And then 5
Okay.
and
plus 5 times 2. Right? See how we work that? That's why it's okay to write it down. A lot of times I will write it out just so that we keep it all in order. Okay? Let's work to the next one. So I need my first row, second column. So now I've got
3 plus
3 times
3.
3, the first ones. Now my second terms,
Negative 2 plus 4.
times.
Oh, sorry. And then plus 5 and times 5.
Perfect. All right? Now, second row, first column,
Negative 1,
times
2. Oh, I'm sorry. Negative 1 times
1 plus,
4 times negative 4.
perfect, plus,
Negative 3 times 2.
perfect. Okay? Second row, second column,
3.
negative 1 times 3
4.
plus 4 times 4
And then 2
plus negative 3
5. Negative 3 5.
times 5. Okay? So you can keep your fingers on them and work it down. Okay? Now that we have this, let's look. We've got 3 plus 8 plus 10. 21. All right? 9 minus 8 plus 25.
That's 1.
26. Right? Negative 1 minus 16 minus 6.
23.
Okay? negative 3 plus 16 minus 15.
Negative 2.
Perfect. So your answer would be 21, 26, negative 23, negative 2. All right. So when we have written out our dimensions, when we've checked and we've already set up to know what our answer should be, if they give you a 2 by 3 times a 3 by 2 and they give you multiple choices and there are things in there that are not a 2 by 2, you can immediately scratch those off, right? They cannot be answers. It has to be a 2 by 2. Knowing our dimensions, knowing what we need to end up with, help us eliminate possible wrong answers if you're on a test. Okay, so turn it over and look at number 5. Can you multiply number 5?
2 by 2. 3 by 2. Yeah? No?
2 by 2 and a 3 by 2. I heard Nathan say it right. Can you multiply these?
No.
No. Middle numbers are not the same. The columns do not match the rows. This is called not defined. Okay? They will use this term. They will not use the term no solution. They will ask you, is this defined or not defined? If it's defined, that means you have an answer. If you cannot get an answer, there is no solution. You can't do it. It is not defined. That is something that you need to know.
So they put not defined.
You would just write not defined on it. Okay? We already talked about the identity matrix and what that looks like. What happens when you multiply any matrix times the identity matrix, you get the matrix again. You get itself, right? So A times 1 equals A, correct? So when we would work through all those columns, you would get an answer times 1, and then everything else would be 0. So you're going to end up with the same answer. That is why it's called the identity. It's the identity property of multiplication. Any element times 1 is itself. So it works the same for matrices as well. All right, determinants. Interesting word. When you have a matrix and it doesn't have a bracket, all right, and it just has straight lines, it can be written DETA, or it will just be written as your matrix set up without the brackets with just straight lines. So this looks like absolute value, kind of. Okay. What that means is that is called the determinant. Every matrix has a 1 number value that is called the determinant. It's kind of like, what does it all add up to? Or what's the whole answer for it, okay? So the number that it adds up to, if I just had a matrix that was a 3, absolute value of 3, my determinant is 3, right? Because I had a single matrix. Okay. The problem is when we get extra numbers in there, how do we figure that out? The way we figure it out is we are going, there's a rule. When you have a matrix, they are set up as A, B, C, and D. Other way the letters go for it. Left to right, A, B, C, D. On it, they will write it as AD minus BC. This is your determinant, right? What it really looks like is we're going to start at the top and we're going to multiply everything down.
So the butterfly thing?
It's almost like cross multiplication.
Oh, sorry, cross multiplication.
Yeah, a butterfly. So we're going to multiply everything down, and that will be our first terms. And then we are going to subtract everything the other direction. You will often see it written with the arrow going up. You will always see it like that. For me, maybe it's my left-handedness, I always go the opposite direction. Because I always think of like a number line, and if I'm going this way on the number line, it's positive. If I go that way on the number line, it's negative. That's why I've just done it like that. To me, that still looks. Because if you graph it, you're like, oh, well, that's going negative wise, and that's going positive wise. So that's why I've always done it that way. So in this one, we would do 1 times 1. Okay? And then we would subtract
2 by 2.
2 times 2. So we'd have 1 minus 4,
It's negative 3.
negative 3. The determinant of A would equal negative 3. They could also write it like this. The determinant of A, I'll give you the little straight lines, okay? It is the number value of your matrix. Okay. Now, what's great about that is it doesn't really matter how big your matrix is. You can always find your determinant. Okay, let's do a practice example of number 3. It says find the determinant. So what would be our first term?
These have little
13.
brackets though.
13 times 2.
Yeah, they left it, but then they said find the determinant. Technically, it should just have the straight lines. I didn't make these notes, sorry. You're right. Okay, so it'd be 13 times 2 would be our first term. We would subtract 8 times 4. So we've got 26
Minus 32.
minus 32 gives us
-6.
negative 6, not 8.
So you put A equals negative.
Negative 6.
Is number 1 0?
Number 1 is 3. It's simply the number inside.
Oh, I thought it'd be 3 and then minus 3.
No, because there's nothing else to do. So a number inside for a single one is simply the number.
Well, that's easy.
That's easy breezy. Alright. So let's look at, I'm going to do a easier one for number 3. Okay, so I have a matrix here. They asked me find the determinant of this one. We use the exact same rules where we are going to add the ones that are moving to the right. We are going to subtract the ones that are moving to the left. However, we have to do all of the numbers to the right and all of the numbers to the left. So I need to have this first column. I now need to have my second column. And I need to have my third column.
I'm looking at 5, right? Or this is.
Yes. All right. So when we get more than a 2 by 2, we have to have all of our columns that we're moving through for our first part. Okay. The easiest way to do this, so that you're not having to jump around, is to repeat your first and 2 columns on the outside of your matrix. All right. So let me rewrite that with different numbers. What did we do? 1, 1, 1. Okay. Because I have to figure out every direction, it would be 2 times 3, and I'd come back here to 1. I've got to group them all together. The easiest way is to start, I've got 1, 2s, and 3s. I'm going to take my first row and I'm going to write it on the outside. Then I'm going to take my second row and I'm going to write it on the outside. This is just to keep it all in order so that you're not getting confused inside the matrix. Okay? Now that I have it set up to find the determinant, we're going to start on the first row and we're going to work our way all the way down. 1 times 2 times 3 is 6. Right? And then go again. 2 times 3 times 1 is
6,
3 times 1 times 2,
6,
6. So I did it easy. They should all be the same. That's why I did it like that. Okay. Now, all of these are added together.
Wait, why is it 3 times 1 times 2 and not just 3?
1 times 2 times 3. We're working our way down. We have to multiply all of the numbers.
Okay.
2 times 3 times 1.
Oh,
Sorry, because my 1's in the wrong spot. 3 times 1 times 2. You have to work your all the way down the diagonal. So if it's a 3, if you've got a 3, you should have 3 numbers in each space. Now, remember how we talked about how on this first one, if we have A, B, C, and D, it was A times D minus B times C, but we only were moving in one direction there.
right, but the numbers on the outside of the thingy.
We don't need it for this one.
But this problem we're doing
This
now.
one we do.
Right. that's
So
what confused me.
here, what we did as we were moving from left to right is that we are finding this singular spot. That's why they need to be all added together. We still need one number for the things that go from top to bottom, and then one that go the other direction, right? So I've got 6 plus 6 plus 6 equals 18. So 18 is all of my information as I have moved from top to bottom, left to right. Okay? So that has given me this first entry. Now, I need to subtract going back the other direction, correct? So going back the other direction, we're going to start, you'll see it like this. We've got this row, and this row. It doesn't matter if you start here and go up or you start there and go down. They're all the same ones multiplicating. 2 times 1 times 3. 6.
6.
Plus 6. Plus 6. Okay? The thing that can get confusing when you're coming back is to start to subtract each one. You are not subtracting each of these numbers. Technically you are. But you are subtracting what they are as a group. Okay? So now I have 18 minus 18.
0.
The determinant of this is 0. Right? What?
Why do we add numbers on the outside?
Because the technical way to find the determinant is to take your first row, so I would go 1, 2, and 3, and then I need my second row down, and then it would be times this first term. So 2 times 3 times 1. Alright? And then this one would be 3 times 1 times 2. But it gets confusing whenever it's all inside the matrix. So it's much easier to just go ahead and duplicate those rows on the outside, and you can keep everything in a straight line.
So which ones do you duplicate when there's not just 1, 2, 3, and there's 3 negative?
We're gonna
5?
do number 5 together. Okay? So let's look at number 5. 3, 4, negative 2, negative 2, negative 1, negative 3,
5,
and
negative 2.
negative 2, 1. Okay? So the first thing that I'm going to do is I'm going to duplicate row 1 on the outside. 3, 4, negative 2. Then I'm going to duplicate row 2 on the outside. Negative 2, negative 1, negative 3. Okay? Now, I've got two things. I've got all of my positives have to be subtracted from all of my negative ones. So on my positive side, I have 3 times negative 1 times 1. So negative 3. I've got negative 2 times negative 2 times negative 2. Negative 8. Right? 5 times 4 times 3.
Negative 60.
Negative 60. Right? Now we're going to take away the ones coming backwards. We're going to work our way backwards. Negative 2 times 4 times 1.
Negative 8.
negative 3 times negative 2, 3 times negative 2 times negative 3,
6, 18.
18. Excellent. And the last one, 5, 1, and 2,
10.
10.
This is so weird.
Okay. So I've got negative 3, negative 8, negative 60. They are all negative, so I add them together and keep the negative sign, right? Negative 71. 18 minus 8 is 10. 10 plus 10 is 20. So I have negative 71 minus 20, negative 91. Right? Okay. A practical version of this is if you have a triangle that is set in a coordinate plane and they're kind of all off and it's not a right triangle, and we know that a triangle is 1/2 base times height, and you don't know those, and you would have to use the distance formula to figure all that out, right? So say this is 1, 6, 4, 1, and 6, 4. Okay? They'll say, what's the area of this triangle? Well, I'm either going to have to figure out the length of a base, figure out a height, and I can do that because I know the distance formula, right? Remember the distance formula?
Not off top.
Square root of your y squares minus your x squared squared, right? Distance formula from that. Or we can use a matrix for this. So I know that I've got 1/2 base times height. I can replace my base with a matrix, and I can replace my height with a matrix. If I was going to write my base as a matrix, I'm going to choose the x's or the y's. We're going to have all of our x terms. So I would have 1, 4, and 6 as my x terms. Okay. I'm going to have all of my, so I have x terms, y terms, and z terms. My y terms are in the same order, 6, 1, and 4. Z, it's all flat in a plane, so I would put 1s in. We can multiply this, and it will give us we find the determinant of this and multiply it, and that gives you the area. So these are some practical ways that you can use it. Okay?
Are you
I'm not asking you to do that.
No,
Just
do you half it because it's not a square?
yeah, because it's not a square. Yep. Okay. So let's go 6. Okay, an inverse. If they talk about an inverse, remember our matrices are labeled with a capital letter. If you see a capital letter with a -1, what did our -1 exponent mean?
It's square.
If I have x to the -1, how do I write that?
Oh, fraction.
You have to drop it to the bottom, right?
Yeah.
So now it's upside down, which that's called the inverse. So if I have a matrix with a -1, they want the inverse of it. Okay. To find the inverse of a matrix, it is 1 over the determinant, and then we're going to switch the letters around. All right? So an inverse is 1 over the determinant, and then we switch these two, and then we change the signs of the other two, right? It's just something that you have to memorize. It's not that hard. Okay, so if we have 1, 2, 1, 2. Let's not do that one. That's 0. 1, 2, 1, 3. First, we need to find the determinant. How do we find the determinant? 1 times 3 is
3.
3. And we subtract going back the other direction.
It's 2, 1.
1. So the determinant is 1. So I have 1 over 1.
How is 1 minus 2 1? I mean 2.
3 minus 2.
Oh,
Remember, multiply left to right, subtract right to left.
3 minus 2.
Yep, so 3 minus 2 is 1.
Oh, sorry. You were doing the. Okay, I'm sorry.
3 minus 2 is 1. Okay, so now I have 1 over, I'm going to plug my determinant in there, 1 over 1, which gives me
1.
1. So do I really need to write anything?
No.
No. Okay. We're going to take our original matrix. We're going to switch our first 2. So now I'm going to have 3 and 1. And I'm going to change the sign of my negative ones, right? Because these are the ones that we subtract. So I'm now going to change sign. So now I'd have -1, -2. This inverse, this matrix is the inverse. If we multiply these two together, we're going to get the number 1. We'll get an identity. That's how it works.
What's a 2 by 2?
Yeah, well, I can have a 2 by 2 identity.
Oh, I thought you meant it was just going to be 1.
Okay, so let's do number 6. It says, are these matrices inverses of each other? So the first thing that we need to figure out is the determinant of the first matrix. So it has 5, 7, 2, 3. What is the determinant of that matrix?
1.
5, 7, 2, 3. Nathan says 1 because
5 times 3 is 15. 7 times 2 equals 14.
perfect. Okay, so it's 1. So does that really adjust anything on my matrix? No. So then the next rule is to do what?
Multiply them together.
No.
Inverse.
Inverse. So I'm going to switch my numbers. So I'm going to have 3 and 5. And we're going to do what to the 7 and the 2?
Negativize them.
Negative. Okay, so is that the second one 3, -7, -2, 5? Is that the inverse of the first one? Yes, it is. Let's multiply it together just to check. We're going to review our multiplication rule. So this is a 2 by 2 multiplied times a 2 by 2. Can we multiply them?
Yeah.
Yes, our answer will be a
2 by
2
2.
by 2. What is our first entry? First row, first column. 5 times 3,
15.
15. 7 times -2,
Negative 14.
Okay, so I have a 1.
Wait.
15 minus 14?
But it's a negative 14.
Yeah, 15 minus 14. Because these are added.
Oh,
These are always added when we're multiplying.
just
Okay, so entry number 2, first row, second column. That's the space that it's in, so I need the first row and the second column. 5 times -7, it's -35. Going to add it to 7 times 5, 35, I got a 0. What is this space? Second row, first column. Second row, first column. 2 times 3 is
6.
6. 3 times
Negative
-2 is -6.
0.
Got 0 again. Second row, second column. 2 times -7
Negative 14.
plus 3 times 5,
15 equals 1.
1. I got 1, 0, 0, 1. Is that the identity matrix?
Yep.
Yes. They are inverses of each other. Okay. Okay. So, practically, solving systems using matrices. Okay. We have 20 minutes. We might not get to the online stuff. Okay. To solve a system using a matrix, we used to do it with linear when we had a linear system, so let's look at that. Our old way for using negative 2x minus 6y equals 0 and 3x plus 11y equals 4, we had two different options. We could substitute, right? Or we could make them the same and use the addition and subtraction. So in this case, we would have to multiply the entire first row by 3. We would have to multiply the entire second row by 2. We would add them together, subtract, solve for one of the variables, in this case y, then we would plug it back in. Correct? Okay. To use it as a matrix, all we're going to deal with is the coefficients. So if we were to look at the coefficients, how would we rewrite them? Negative 2, negative 6, 3, and 11. Right? You got that? Basically, we are taking those coefficients and multiplying them times x and y. So that's how it's written. And that equals 0 and 4, our answers. So do you see how we have taken each of our numbers and we've rewritten it as a matrix? Correct?
That's all we have to do?
This is how we're setting it up. Okay? This will help us solve. Now, if I had this as a basic equation and I had 3 times x equals 4, what do? We've learned it as divide by a 3. X wants to go to the movies by himself, right? We divide by 3, we divide both sides by 3. It is the same as multiplying each side by the inverse, correct? When we multiply by the inverse, we end up with the number 1, which simply leaves us our answer. So in this case, since we have set up as a matrix, and I want to solve for my x and y, I want to know what they are, I need to get rid of this first matrix. The way that I get rid of it is to multiply by the inverse. Does that make sense? If this was 3 and this is x and this is 4, to get rid of my 3, I would multiply by its inverse. But what I do on one side, I have to do on the other side. So I know immediately anything multiplied by its inverse gives us the 1. Do I really need to work it out on this side? No. It's going to end up being the number 1. So I know I'm going to end up with my x and y by themselves here. Okay. This is the part that I need you to understand, that order matters. So technically, I am multiplying first by my inverse, which means that on this side, I have to multiply by my inverse first. And then, so we've always just kind of put it on the back side, but the order matters. Remember how I was saying like A times B does not always equal B times A? So you're multiplying your inverse on the front end here to get rid of your matrix. So I need to multiply my inverse on my front end to get rid of my matrix. Otherwise it doesn't work, right? So then our question is, what is the inverse of this matrix? How do we find the inverse again?
Reverse, or no.
We need to find, first we need to find the determinant. So what is the determinant? Negative 2 times 11, negative 22, minus
18.
negative 18.
So plus
So my determinant is
negative 4.
negative 4. So my inverse is 1 over my determinant. And then we are going to switch these, right? So I have 11, negative 2, and then I change the signs of the other one. Now this goes back to the thing we learned at the very beginning. We have a scalar multiplied times each one. Right? In this case, I'm actually not going to multiply it through because I want to do it on a different one. Okay? So I know that I've got 1/4 times 11, 6, -3, -2, and then my answer matrix. Right? See how we rearranged? So I multiplied the first one times the inverse, so I got a 1. Now my second side is by the inverse. This is the inverse matrix times my constant that was on that side. Now because this is a scalar, it can move. So is it going to be easier to divide or multiply each of these elements and entries by 4, or is it going to be easier to do the second one? It just has to go to one of them. This way I'm going to end up with a whole lot of fractions.
Yeah.
If I use the 1/4 with this one, I get
0
and
1.
and that was a negative, sorry.
Yeah.
0 and -1. That was much easier, right? So now I've taken care of using up my -1/4. Okay. Now I simply have multiplication. Can I do this? This is a 2 by 2 and a 2 by 1. We can multiply them. My answer will be a 2 by 1. Okay. First row, first column, 11 times 0, 0. 6 times -1, -6. Okay. I don't have anything else, right? Because I just have a 2 by 1. Second one, -3 times 0, 2 times -2 times -1, 2. X is 6, Y is 2. So in this case, we could have solved it, right? And had -6, if I did times 3, minus 18y equals 0, and 6x plus 22y equals 8, -4 y equals 8, y equals -2.
Wait.
Y equals, what did I miss at one? 22, oh, that's not -4, sorry. Y equals 2. So in this case, this one was pretty simple to do it that way. I got the same answers. When we get to the triples, this is way faster versus solve that, mix them together. Okay, so this is why you can use a matrix to solve a system of linear equations. Okay, we're going to work through the one on the back. You might want to take notes.
What is R?
Okay, this is called, there's a shortcut for this. So we just went through all of the steps of multiplying through, doing an inverse, and getting those answers. There is a shortcut or an equation called Cramer's rule that will get you a specific variable every single time. And so I'm going to write out the first one. We're going to work through this problem. If you are asked, what is z? Okay? And they only want you to solve one. In other words, we've got to use all of our, group these, group the other ones, find an answer, right? Okay, we can use a matrix to find a specific variable, a specific answer. So on the one that we just worked through, we got the answer for both x and y. We can use Cramer's rule, which simply uses the determinants of the matrix to find a specific one. So for a smaller one, like we just did, you have A, B, C, and D. So like the equations that we just worked through with 2 variables. Okay, you can find when we set them up, right, we made this into a matrix. the determinant of your original one will always go on the bottom. Okay? This is Cramer's rule, your check for it. Then you are going to find the determinant of a top one where you replace your answers into whatever variable space you were looking for. So if I am solving for x, wherever I have my x values, I'm going to put my answers 0 and 4, and I'm going to leave my y values. This will immediately give you the answer for x. So what is our full determinant for the one we just worked through? We decided it was negative 22 minus a negative 18, so it was negative 4, correct? So my determinant on the bottom is negative 4. What is the determinant whenever I replace my x values?
20.
Negative 24?
Yeah.
Plus, sorry, probably just 24 because it's minus a negative 24. Negative 24 divided by negative 4? Negative 6, isn't that what we had gotten? X equals negative 6.
Wow.
Super shortcut. So now, let's see if we can use this shortcut for this big system. Because you know what it looks like to solve this through elimination, correct? Let's see if we can work it with a determinant. So let's work through our numbers. We have 1, 2, negative 1. Everyone see how I'm getting the coefficients? Negative z is really a negative 1. Negative 3, 2, 1. This one's tricky. This is my x, y, and 0. X is 1. What is y?
0.
0. I do not have a y value. It is 0. What is my z value?
2.
2. Perfect. This is my base determinant. How do we find it? We're going to duplicate our rows across.
1 times 2 times 2 equals
4.
2, that's 2. And then negative 3. Or no, positive 3.
Plus 3. Okay.
Wait, no, 0.
As 0. There you go. Now we're going to work our way back.
4 times negative 12.
Perfect.
0.
0.
Negative 2.
Negative 2. So I have 6 minus
Negative 14.
negative 14,
20.
20. My determinant is 20. This will be the same no matter which variable we're solving for. So we know right away, my determinant's 20. So I'm going to make a note up here. Now, I would like to solve for z. Z equals what? My determinant is 20, so I write it on the bottom. Okay. My new matrix on the top, I'm going to take my answers and plug them into my z column. So x stays the same, 1, negative 3, 1. Y stays the same, 2, 2, 0. Z now becomes 5, negative 5, 0.
Oh, okay.
And I'm going to find the determinant of this. Duplicate your first and second row out. We've got lots of zeros in this one.
It's easy.
Okay? What's our first one?
0.
We have 0 plus
Negative 10.
negative 10
0.
plus 0.
Plus
Okay? Now I'm subtracting
0.
0,
0.
0,
10.
10. So I have negative 10 minus 10,
Negative 20.
negative 20. So I have negative 20 over
20.
20.
Negative 1.
Z is negative 1.
Wow. And then you can solve the bottom one.
Yeah, if you want, now x equals
Negative 3. No, negative 2.
2.
Negative 2, because you have to move it over. No, it's negative 1. Oh my goodness.
2 times negative 1,
Yes.
negative 2.
Yes.
2
And then-
minus 2
then you
equals
move
0.
it over and
X equals 0. So x now equals 0. So, did the matrix make solving this one easier?
yes.
Okay. If it is a if there are 4 equations, exactly the same. You find your determinant of your original 4, and then you replace your answers into whatever variable you're finding. Do we see how this can be beneficial
Yeah.
to save us some time? Okay, we've got 6 minutes left. Okay, this is called Cramer's rule. C-R-A-M-E-R-S. Cramer's rule. Okay. So it is often written something like that. Right? So you can still solve it the old ways. On your system it says use a reduced row echelon format. We are not doing that. That is the same as originally where you multiply through to make them equal and then you're adding them. To me, it doesn't make sense to do that with a matrix when you could just do it with the linear system. Okay, so I have, okay. Let me pass out your papers. You have a short,
You do know it's spring break, kind of.
yeah, next week's spring break, yes.
No, you got it.
Absolutely.
Kind of.
Here, I'll give you, Micah stuff.
Okay.
Okay, on the first one, matrix assessment, scratch out that scratch out the -1. You don't need to find the inverse of that.
-1.
Yeah, it's just A. Okay,
Which?
so it says, we're going to create a secret message. Okay, so you're going to be multiplying the 3, -2, -1, 1. So your A matrix times each of those variables. You are doing times B, C, D, and E. They have it written for you at the bottom. Okay. Then you are going to line them up on the back with the answer for B, C, D, and E in order. B's answer, C, D, and then E will be written in order, and they will each have a number. It will spell something. You will go down and across. Okay. So because you have a 2 by 2 multiplied by a 2 by 1, each of your answers should be you have a 2 by 2 multiplied by a 2 by 1. So all of your answers should come out into being what? A 2 by 1. Okay, so there's that one.